programming as a standard practice, where one person writes the code and the other person sits there watching them write the code and getting them to explain why they're writing the code in a particular way. It sort of is a form of software inspection, right? So they're looking at and they're questioning every design choice that goes into the code implementation of the person who's doing the typing. It can be a really valuable experience for both people, and I would encourage you to do this when you work on your team project. You need to be proactive in questioning the person who's writing the code. So why have you chosen it to do it that way? And getting them to explain. Right? Talk about the decisions they've made in terms of the algorithms they're using or the data structures they're creating or anything like that. And not being super critical or anything, but a good term for it is a critical friend. Okay, so being helpful, asking questions and offering constructive criticism of what they're doing. Is there anything I've already said? Okay, so software inspections, I guess this point here, that you don't have to do it just for the actual code that's being written, though. You can do it looking at any stage of the software engineering process. So all of your documentation that you're building up along the way, whether it's user stories or a formal requirements document, a formal architectural design, anything like that, you can look at it and say, so why have we made this decision here? What are the implications of this decision that we've made? Would we be better off doing it that way rather than this way? That type of thing. So the advantages of inspections. Well, first of all, when you're testing, as in not doing an inspection, but actually running the program, sometimes an error, an obvious error, will actually hide the fact that there is a deeper level error underneath. So you just see the surface level error, and you don't see that deeper level error. Because inspection is static, you don't have to worry about those interactions between the different parts. And you're more likely to notice both levels of error than you would during a test, which was probably going to only reveal one. Of course, after you've fixed that one, you'll run tests again and then you'll discover the other one, but then it's a two-stage process. Whereas with an inspection, hopefully you'd be able to find both problems straight away. Of course, with inspection, because you're not running it, you can do it on something that's not yet complete. Okay? We should be designing test cases so that they can be run and sort of put stubs of program around them and do some testing before the whole program is complete anyway. But inspection is far more flexible in that respect. Okay? And this is an important part. So as well as actually looking for program defects, so what's wrong with it, it can also consider broader quality attributes, like is it complying with the standards that we need to? Or is it portable? Are we going to be able to use this on a different platform if we need to? Is it maintainable? Is the code well written so that if somebody else comes along in 5 years' time who wasn't in this original development team, are they going to be able to learn it quickly and get up to speed quickly? Okay, so there are advantages, definite advantages of inspections, which is why they're complementary to testing, not one or the other. Okay, so going back to this diagram that I had up before, oh, sorry, the circles don't show up very well, but what I'm going to do now is to step through each type of testing that's in this diagram. So first of all, focusing on the development testing. Unit testing is often the biggest part of your testing process as you do your software development. And this is where you're testing individual program units or classes. And your focus is on testing functionality of the objects or the methods that you've developed. So you write really small test harness for whichever object you've got, just to make sure that every method that you've implemented within that object does exactly what you're expecting it to, that you're not getting things, you know, like if you're using a programming language like Java that does data hiding using public and private things, that you haven't got things that should be private which are public, and vice versa, that type of thing. Once you've done your unit testing and you're satisfied that all your things are performing individually as you expect they are, you start doing integration testing, or component testing it's sometimes called, where the individual units that you've already done the unit testing on are combined and tested. And here what we're focusing on is the interfaces. Okay? So how those different objects or whatever communicate with each other. This is really important if you've got a reasonable sized development team where one part of the team have done one set of the things and another part of the team have done another set of things, and they've assumed that they talk together in certain ways, and then you put them together and you realise that actually they misinterpreted what those interfaces were going to be like, and there has to be some adjustment. Right? Automated testing is not separate from these things. It's a really important thing to do if you've got any sort of program of scale, because you can't manually test over and over again as your product grows. What you need to do is to create scripts or use something like JUnit that will automatically set up tests to be run, and every time you want to run the tests, you basically just click a button or type a command on the command line, and that whole set of tests gets run, and all of the outputs are stored and any anomalies are flagged, and you can test it over and over again. Right? With automated testing, it's not like a level of testing like the other things. You could use it for unit testing, you could use it for integration testing, you could even use it for system testing, which is testing the system as a whole. Right? So we're here looking at basically the smallest level of testing. Here, looking at very close interactions between units. System testing is where we're starting to look at the interactions, so not just the interfaces between things, but if this module changes data in that module, and this module uses data in that module, and changes it sometimes as well, you know, does the thing as a whole perform as we expect it to? That type of thing. Regression testing is another type of whole system testing, where it checks that when you change any part of the system, all of your previous tests still work, basically. Because sometimes you can change one thing, and you're thinking you're just fixing this little bit of the program, but this bit over here depended upon it, and all of a sudden this little change that fixed this little thing breaks that thing over there. Right? So that's why regression testing is so important. You need to go back and test everything you've tested before, just in case a small change that you made breaks something unexpected. And finally you get to beta testing. Again, this is another whole system test, often with the end users, where it's the last phase of testing before a formal release. Okay, so I don't know how many of you use beta versions of software. You often get invited, you know, if you use Facebook or something like that, to try out this beta version. And the idea is that there might actually still be a few bugs in it, but you get first chance to look at all these new features, and if you discover one of the bugs, you provide the feedback to the developers, and it gives them the chance to fix it before it goes out to the general public. So you take a risk by using beta software, because there could still be problems with it, but the developers are fairly confident that they've fixed all the problems. Okay, you only get to beta release if you're pretty sure you've got a candidate for actual release. You're not expecting to find bugs, but you just want to make sure. automated testing, as I've said, wherever possible, you want to automate it so that you can check it without intervention, particularly at the unit testing level, right? Because you're going to have lots of units within your software, and the last thing you want to do is to do every single one of them manually every time you make a change. Okay, so instead, from the first go, start writing scripts that are going to do the testing for you so that you have that script. The first time you do the test, you have the script and you save the script, and the next time when you have changes made, you run the same script. Okay? You might enhance the script to do more testing than you had in the original case, but it's the basis of an ongoing testing process. Okay, so as it says, you use an automated framework. JUnit is the one that's usually used with Java-based things. Most IDEs for Java will include support for JUnit. And we'll look, if you haven't, I don't think you've done it this semester, have you? Use of JUnit. Yeah. So we'll look at it next semester when we do the software development project, because you'll need to use it there. Okay, so we'll do some formal classes on that. And basically they have generic test classes that you extend to create specific test cases. So again, we're using design patterns. Okay, it's working on the assumption that the classes that you're building are some way similar to other classes that have been built before, and because they're some way similar to other classes that have been built before, the test cases that you're going to use for them are in some way similar to those other classes as well. Right? And then basically, you run all the tests that you've implemented and report, often through a GUI, on the success or otherwise of the tests. So sometimes you've got a GUI for it, other times it will just get saved to a file and you have to inspect the file. In general for testing, you want to choose inputs that will force the system to generate all error messages. Okay, so you're expecting that there will be times when you get erroneous input for some reason, particularly if you're writing a user interface. Users are guaranteed to put in the wrong thing at some time, either accidentally or because they didn't understand how to use the system. And what you need to do is to give them meaningful feedback to say, not just error, wrong input, but explain to them why it was wrong and suggest what they might want to put in instead if you can. Sometimes you won't be able to make that suggestion, but if possible, you should. You want inputs that are going to cause input buffers to overflow. Okay, so what's an input buffer? Well, if you've got large streams of data coming into your program and they need to be processed, that's an example of an input buffer, right? So if you're dealing with big data, that's a classic example where sometimes the data comes in more quickly than you can actually process it. Right? But another example of an input buffer would be just reading in a file. Right? If the file gets very large, can your program still handle it, or does it run out of memory space? If the user is typing something in, is there a maximum length to the thing that they can type in? And what happens if they try to go over the maximum length? So anything like that, which involves a series of something going into the program. Okay, and something could be characters, could be bytes from a file, could be data streaming from another source, from sensors in the weather data set example. So, you know, what happens if you get an erroneous sensor that instead of sending a small amount of data every 5 minutes or something, so suddenly starts streaming huge amounts of rubbish. Does it break your program? Or does it degrade gracefully and say, well, that doesn't look right, I'll just ignore that input or something like that? You want to repeat the same input or inputs numerous times in many cases, because sometimes the first case of something being input is absolutely fine. But then because that gets processed somehow and then more data comes in and that sort of thing, sometimes loops build up that cause problems. So you don't want to just test it once and assume it's okay. Test it a few times. And a few times is going to be something which you need to test, to judge on a case-by-case basis. And you're going to get more experienced at it as you go along. That's really the case of it. Okay, so there is no golden rule. Typically, when you're working on a software engineering project, you'll come in as a junior software developer, and you'll have experienced team members around you, and you'll learn from them. Okay, so it's a collaborative process working out how you're going to do it. You want to force invalid outputs to be generated, okay, or try to. Ultimately, you don't want invalid outputs to be generated, but do everything you can to try and get them to come. And if you try everything you can and you don't succeed in generating invalid outputs, it gives you a lot more confidence about your program. But again, still doesn't guarantee that they're never going to be there, because you can't think of every possible case. Force computation results to be too large or too small. Okay, so what happens if the result of your computation is a really large number, too large to store in a standard data type? What happens if the result of your computation is so close to zero that it's treated as zero and you end up with a divide by zero in your calculation? That type of thing. Okay, so these are general testing guidelines, and they really apply to every phase of testing, from unit testing right through to system testing. Not for beta testing, because beta testing is with the users. Not for customer acceptance testing, because again, that's with the users and so on. But everything up to beta testing. So we mentioned test-driven development very early on when we were starting to talk about the development phase of software engineering. And as we said, test-driven development is an approach to program development where you interleave the testing and the code development, and the tests are written before you write the code. Right? So passing the tests that you've written is the critical driver of the code that you develop. Every time you develop more code, you test it against the test you're meant to be testing against. And you have an incremental thing. So first of all, you start off small. You've got a small test to test the unit again. Right? Pass that test. You develop and test another unit. Pass that test. Then you test them combined to do the integration testing. Hopefully pass that test. Right? But at some point, you're going to fail tests, and you need to go back and revise. Now, if failing the test means that you need to revise a particular unit, you've got to start from the bottom again, test that unit, then do the integration test, then eventually do the system level. So you're always building from the bottom to the top when you're doing the testing. As it says, it was introduced as part of agile methods, particularly extreme programming, but you can use it in a traditional plan-driven development process as well. Okay? And in some senses, it fits very well with a traditional plan-driven development system, because plan-driven development has a really clear picture of what you're setting out to achieve ultimately. So you can easily write those tests before you do the implementation. So if you're doing test-driven development, you start by identifying the increment of functionality that's required. Okay, so what are we going to be, what do we need to test with this implementation we're about to do? And it's usually something that's quite small and implementable in a few lines of code. So we're talking about small-scale testing here, small-scale implementation. You write a test for this functionality and implement it as an automated test. So very explicitly, this is about automated testing. And, well, there's a step missing here. In between implementing it as an automated test and running the test, we need to implement the functionality, right? But once we've implemented the functionality, we run that test and all of the other tests that have been implemented, right? Once all the tests run successfully, you move on to implementing the next chunk of functionality, which again involves writing a test for it, and then testing, adjusting, and then going on, right? So very much interleaved. Okay, so they all fall in to this far left-hand side of this diagram here. Unit testing, integration testing, and automated testing. Still part of development testing, though, are these system-level testing ideas. Okay. So we had. Where's my slide on regression testing? No, I mentioned regression testing, system testing, and beta testing. Yes, sorry. Before I talked about test-driven development, sorry, that's right. So now we're moving into the release testing, okay? So they involve the regression testing, system testing, and beta testing just as they do in the development testing. Okay, so it's kind of like the overlap phase of the testing, where we move from the verification to validation. Not just, is each bit working as we expected according to the requirements that we had specified, but are we actually satisfying the customer with what we've developed, right? So beyond the regression testing, system testing, and beta testing, first of all, we have a customer acceptance test, where the customers test a system to decide whether or not they're going to accept this as a valid interpretation of what they ordered, basically. So originally they signed a contract with the developer to produce something, and this is where the customer's saying, yeah, that satisfies what we've signed the contract for, or no. Yes?
Is the beta test done before that?
The beta test is often done before that, and it gives a chance for them to iron out. So the customer acceptance test is a pretty critical stage of the testing. It's basically where they will sign up to release the final funds for the project. There'll be some funds available for maintenance afterwards, but basically it's a critical stage in a contractual term. So with the beta testing, there might be things that don't quite meet the customer's requirements, and that is part of the beta testing process for them to say, this isn't quite what we wanted or intended, and you need to fix this before we're going to get to that stage. Because if they fail the customer acceptance test, there's usually financial implications for that. Okay, so it might lead to a reduction in payment, or it might lead to funds being held back when they're expecting them to be released, that type of things. Right? So yes, the beta testing usually does come before customer acceptance testing. Okay, in a sense, the beta testing is sort of like soft customer acceptance testing, whereas this is a very formal, hard deadline. Okay, we also have usability testing at this stage. Okay. Usability testing, some aspects of usability will get put into the non-functional requirements, okay? But people are really bad at knowing what they need in terms of usability until they actually use it. Right? You don't realize how bad something is for your users until they're actually using it in practice. So usually what happens is it happens after the customer acceptance test, in the real environment, after it's been deployed to the customer, And there'll be a phase where they have the chance to say, it's really annoying when I'm on this page that I've got to click through 3 other pages if I want to change that detail because I'm changing that so frequently. That's the type of thing that you get when you do the real world user testing, because the requirements might have captured the fact that a user on this page might want to change some other piece of linked information and they have to click through to it. But they might not have realised that it was a frequent occurrence. They might have thought that it was going to happen only once a week or something like that. And so they think, well, it doesn't matter that it's 3 pages away. That type of thing. And yeah, even a case where, you know, you'll have one set of users who are heavily involved in the requirement solicitation, but then you have another class of users who were only sort of peripherally consulted, and so their needs weren't fully taken into account, that type of thing. So there'll be a period of adjustment, and looking at also where they were interacting with external systems. When they've been tested in the lab, they'll have used dummy data for those external systems, okay? And they won't necessarily have a good idea about the types and volumes, etc., of data that are going to come in from those external systems, and possibly because it's, you know, sensitive data or something like that. And so they need to make sure that those interfacing with those external systems is not having a significant impact on the performance or whatever the software that they're using. Okay, and the other aspect of release testing is the performance testing. Okay, related to what I was just saying there. Many of the non-functional requirements aren't going to be properly tested until a release candidate is available, because the non-functional requirements are going to be things about the memory usage or the speed, processing speed, or the downtime and that type of thing. Till everything gets together in a complete system, it's pretty difficult to measure them. Right? So you can measure the processing speed of component parts, but when they start interacting with each other, you don't know what sort of lags that's going to put on the processing, things like that. Okay, so without actually having implemented any software in this module, it's very difficult to talk about testing in more detail than this. But we'll come back to it next semester when we're doing the actual practical module. And hopefully you have sufficient Java skills now that that's going to be relatively straightforward for you. Right? But we'll have, again, a lot of more practical oriented lectures associated with that module. Any questions? Yep.
Yeah. So usability and performance testing is done after customer acceptance test.
I haven't they're not necessarily in order, okay? So you could put usability testing before customer acceptance testing as well, okay? Depending upon how highly integrated it was into the contractual agreement, the usability of the system. So they're not necessarily in that order.
If it's put after, then customer does the testing?
Sometimes it's only possible to do the performance testing in the actual environment, particularly if they're interacting with other systems and the performance is going to be dependent upon the interaction with those other systems. So sometimes it does have to be after it's been deployed to the customer. Okay, it depends what those non-functional requirements are, very much. Any other questions about testing? Okay. In that case, I'll move on to the software evolution part of the lecture. So starting off with software change and maintenance. So we've said all along, software change is inevitable. Okay, new requirements emerge when the software is used. The business environments change. It's probably the biggest driver of software change and maintenance. Errors must be repaired. Okay, so bugs are always appearing in software after it's been deployed. New computers and equipment is added to the system. So, you know, you start having to either operate with new hardware platforms or get information from new systems and integrate that and that type of thing. And it's kind of related to the business environment changing, I guess, but the performance or reliability of the system may have to be improved over time, just because things change, expectations change, and we have to deal with that. And software systems are critical business assets, right? They have to evolve with the business, otherwise you'll end up with a business which is a dinosaur basically being held back by its software systems. And as a consequence of this, the majority of the software budget in large businesses is actually devoted to changing and evolving existing software, not developing new software. It's about getting what they already have bigger, better, faster, performing to meet their needs. Okay? Occasionally, you will get them developing a completely new radical system, but it's a high-risk strategy, and most companies will avoid it at all costs because of that. So the software evolution process depends first of all on the type of software being maintained, also on the development processes that were used and are being used. Okay, so they're not necessarily the same thing. A piece of software might have been developed using standard software engineering practices, and then the company switches to a more agile approach. Or it might have been developed with an agile approach to start with, and then the maintenance team is more used to a traditional software engineering approach. So you get changes like that. And also the skills and experience of the people involved. So somebody who's been working with the same company for 20 years and was there when the software was originally developed and installed is going to have a wealth of information in their head that probably isn't on paper anywhere, which is going to make the maintenance and future upgrades to the system a lot more easy, just because they've got that knowledge. But then that person retires. That makes a huge difference to the company, right? And they often don't realise until the person's gone. Proposals for change are the driver for system evolution, and you need to understand all of the components that are going to be affected by the change when you do the costing of that. So if you go, yeah, I really want to change the purchasing system so that it's easier for the people to use and so that invoices go out more quickly. How's that going to affect everything else in the system? How's it going to affect the say the stock maintenance level system? How's it going to affect the way that people give quotes for things and that type? So there's going to be all these sort of related systems that are interacting with that one, and how's it going to impact upon them? Okay, so this whole process of change identification and evolution continues through the system lifetime. Pretty well from the moment it's deployed, people start saying, oh, wouldn't it be great if it could do this as well? You know, I love this new system, but I really wish it did that. And so people are already starting about the next enhancement to the system or something like that. And then 10 years down the track, they go, I love this system, I've been using it forever. You know, I know that it's slow and it's a bit painful, but do you think if we looked at optimizing this bit here, it would actually speed it up? So they're not necessarily, 10 years down the track, they've probably got most of the features that they want. They're very used to the system they're using, they're comfortable with it. They're not even going to necessarily have the vision to see what could be added to it because they've become so familiar with it and used to it. But they will recognise that there are bits of it that aren't performing well. And so the maintenance and evolution goes into the process of making those bits perform better. Right? So if we're looking at implementing change in a software system that's been deployed to the customer and may have been in use for some time, we still need to go through this process of design, implement and test and release, right? But a critical difference is that the first stage of the change implementation might actually involve program understanding if you don't have a clear picture of how it was developed in the first place. Okay, so often, if it's 10 years down the track, it's going to be different system developers who are looking at implementing this change to those who originally built the system. So during that program understanding phase, you're not doing your traditional requirements elicitation. You're looking at the program itself and understanding how it's structured and how it delivers functionally, and critically, how the proposed change might affect the program and particularly other parts of the program that you hadn't been thinking about as being affected by the change. Okay, because if they're really tightly coupled between different parts of the system, a change in this part here might have significant impact on a change on the system there, kind of thing. There are lots of different types of maintenance, falling into three key areas. First of all, and perhaps the one that's most obvious, are fault repairs. So if you detect a bug or a vulnerability, security vulnerability, for example, then you need to correct the deficiencies. Okay? So we need to ensure that the program performs as it does, and when it doesn't, we need to fix it. Next is environmental adaptation, where we recognise that we're in a changing environment. So we're changing a system so that it operates in a different environment from its original implementation. So you might be changing the hardware that it's running on, or it might be an upgrade to the operating system, which means that the system calls have changed slightly or something like that, and you have to deal with that. You might have different peripherals attached. You might have the external software that it's communicating with has changed slightly, and you need to do those sorts of adaptations. And then the final class is the idea of functionality addition and modification. So I'd like to be able to do that as well, or I'd like to be able to do this a bit differently to the way it's been implemented. Right? So not a full re-implementation of the system, just looking at doing parts of it slightly differently. Typically, this is kind of a pie chart representing the entire maintenance effort. About a quarter of it goes into fault repair, about 20% into environmental adaptation, and about 60% into modified functionality or addition of functionality to the system. Okay, so this is over the lifetime of the software, which could be 20, 30 years or more. Now, maintenance costs are typically much greater than development costs, from about 2 times up to about 100 times more expensive, depending upon the application. It's affected both by technical and non-technical factors. So what I mean by that is, so we have the technical factors, which are like the programming language that was written on, the hardware that is being used, all that sort of thing. Non-technical factors are users, right? The environment, about when you can do changes, you know, does downtime have to happen in the middle of the night, all that sort of thing. The costs increase the more the software is maintained. Typically, maintenance will corrupt the software structure. So the original designers will have had a nice, neat, clean design, hopefully, if they've done it properly. But each little tweak that happens after it's been deployed will suddenly change that nice, clean design structure, and over time get more and more ugly and messy, and bits here that are related to bits way over there and that sort of thing. And basically, the more that happens, the more difficult the maintenance becomes. Right? Aging software particularly can have high support costs because, for example, you have old languages where it's very difficult to find people who have that knowledge. Okay, so there's still a huge amount of software out there written in COBOL and Fortran, and hardly anywhere teaches those programming languages anymore. Okay, and they're ugly. I've never learned COBOL, but Fortran is ugly. Even finding compilers for old hardware can be a difficult thing. Okay, particularly if it's an unusual language, but even if you're looking for a compiler, like a C compiler, for an old piece of hardware, it can be difficult to source it. So it's usually a lot more expensive to add new features to a system during maintenance than it is to add those same features during development. Because when you add them during development, you've still got control over the entire design of the system. You can make adjustments so that they fit in a sensible way. Once the system's actually been deployed, you've got to work with what you've got. It's very difficult to make major changes. And that brings me on to the idea of legacy systems. Now, legacy systems are older systems that rely on old languages and technology. They're the dinosaur in the house, and a lot of large companies have them. Because they're not just software systems, they're broader socio-technical systems that include hardware, software, and business process. And sometimes that software has become so heavily integrated into their business process, the whole way that the company runs, that it's very difficult to get them to let go of it and replace it or something like that. So diagrammatically from the book, here's a picture of what that might look like. So we've got the application software, which embeds knowledge of the business policies and rules, and these constrain the business processes which use the software. The software also uses application data, and it runs on this obsolete old hardware. It also uses support software, which has to run on that old system hardware as well, even though it may have been written a lot more recently than the original application software. Somebody's had to work out how to implement it on this whole system hardware. So you've got this whole big network of things that are all interacting with each other, and it makes it very difficult to change one part of it. Replacement of these legacy systems, because they are so integrated into the business process, is very risky and expensive. Okay, so if I'm going to build the complete software system for a business from scratch that's been running for this business for 30 or more years, 40 or more years even, what are the chances that you're going to get every detail into it? Right? It's going to be a huge piece of software. So for example, banks are the classic, right? There are a lot of new banks these days, but there are still a lot of banks that have been around for a long time. They developed software in the 60s, and elements of that software is still running. Right? It's very high risk for them to try and replace that software, because if something goes wrong with the replacement, it has major financial implications, basically. But it means also that dealing with change is tricky. So programming skills are lacking. So that old bank software is often written in COBOL, and hardly anybody learns COBOL anymore. Right? Although interestingly, the institution that I used to be at has just reintroduced a COBOL course to address that lack, so that there are people graduating who have that knowledge. Often with the old software, they're very poorly documented because they were written at a time when software engineering processes weren't well developed, and people just didn't have that vision that their software was still going to be used in 20 or 30 or 40 years' time. They thought they were writing something that was going to, at most be around for 2 or 3 years, and then somebody else would write something and replace what they were doing. They just didn't have that vision for what was going to happen with their software. You get that issue with system structure degradation that I was talking about before, because this software has been around for so long, it's been maintained for so long, there have been bits changed and patches put here, and this security flaw is being fixed, and that additional feature has been added, and they all end up with this big mishmash of things. There will also be a lot of optimizations that have been put into the system, where they've done certain things to speed up the processing power or the memory usage or the way that data is stored to reduce the disk usage or something like that. And you look at the code and you think, I have got no idea what this is about, because it's using some technique that was the obvious way to do things in the 1970s, when you were limited by magnetic tapes for data backup, and these days the same sort of constraints don't apply, and so people just aren't familiar with those optimization techniques. Anyway, essentially you have 4 possible management strategies. So first is scrap them entirely and modify the business process to deal with the fact that we're going to have a new system, and the business process that was built up around the old system was probably not the best one. It was, forced upon it by the software that was being used, and if we have a completely new set of software, we can do things differently, and that will be a good thing. So that's one way of going about it. This way. You can continue maintaining the system, okay? So have an in-house team of people who know stuff about that programming language, about that hardware, and constantly recruit people to that team who you're thinking when they come in they're not going to have knowledge, but they will get trained in-house to support that system. You can transform the system. Okay, so start working on bit by bit and eventually evolve into something that is better suited to your business needs, or and no longer using the obsolete languages and hardware, etc. that you were doing. Or you can replace the system entirely. So this is similar to the first one, except in this case we're basically going to say, okay, we're going to try and re-implement it using modern technology, but keep the same business process surrounding it.
And which one of them has the lowest cost?
Well, it really depends upon the legacy system and the business surrounding it. Okay, so you would have to do it on a case-by-case basis. Right, so I'd say for a banking system, probably the lowest cost there would be continue maintaining the system, because you would have a reasonably large team of people doing software support and maintenance, and you can recruit into that team, and training people actually is not that high a cost associated when you've got a large team, right? If you were talking about a more specialized business that would benefit very strongly from a transformation of their business process, that one might actually be the lowest cost overall. Risky, yeah, right? So you need to factor in that risk cost, but the benefits to be obtained by transforming the business process might outweigh the risks, right? Replacing the system. Here's an interesting one. And it really depends upon what the system is that you're replacing. Because if it's banking system, there's so many different elements of that system and so much interaction between those different elements. It might be really hard to work out exactly what's going on in the existing system. There's probably nobody who's got an overall picture of the system and a good understanding of how the different parts interact. If you're talking about something a bit smaller scale than that though, where there's a reasonably good understanding of the system, then replacing the system might be a viable and cost-effective way of doing it, right? I was involved in a project like, well, I was peripherally involved with projects like that, but I wasn't involved in replacing the system. I was developing some new software which originally had to interact with the old system, but while I was developing that new software, there was another team who were replacing the old system. And they were replacing like for like, but with a newer modern programming language to work on new modern hardware. Right? In that case, it was a Fortran-based system being upgraded to use modern technologies. So again, if you've got that good understanding of how the original system was built, then that might be a possibility. Okay. Sometimes, if you've got the original source code, you can do automatic source code translation, and it's not perfect is the problem. You've then got to go through and do all the testing and stuff again. Okay. And also automated software generation code produces really ugly code, which is unreadable and difficult to maintain. So it might be, in some cases, better to do it by hand, to rewrite the code by hand. It depends upon the size of the system. You know, if the system is tens of thousands of lines of code, that's feasible. If it's hundreds of thousands of lines of code, it's a bit hard to do a full translation of the system, right? So, without knowing what the system is, it's difficult to say which one's going to be.
Is it something that the developers should write in the documentation? Let's say that this is the best maintenance strategy. Yeah.
So if we're talking about developers with legacy systems, you would be talking about the senior software engineers. Okay. So it would need to be made a decision at a very high level in collaboration with management, because remember, these are socio-technical systems. It's not just about the software, it's about the way the software fits within the company's organisation and how it affects the business processes and that sort of thing. So it would have to be a very high level strategic decision about what the best choice is, with an understanding of not just the software, but how the software is used and how it affects the way the company runs. Okay, so another way of doing this categorization is to look at the categories of legacy systems. So if they're low quality and have low business value, then you can easily just go, well, we can just scrap that. Because if it's really badly written and it doesn't have much value for the company, we just either get rid of it entirely or replace it with something that's going to work better and be better. If it's low quality and high business value though, they're important to the business, but they're expensive to maintain. So ideally in such cases you would either re-engineer them, so go through and with the existing software that you've got, try to refactor it. Remember we talked about refactoring, this idea about changing the structure of the software to something that's better suited to its needs, or completely replace it if a suitable system is available, can be developed. If it's high quality and low business value, well, that's an odd position to be in. It's probably high quality in that case, because it's never really needed to be maintained, so there haven't been many changes to it, and it's reflecting its original design structure or something like that. So in this situation, you can either replace it with COTS, stands for commercial off-the-shelf software, scrap it completely. Okay, so if it's not really being used much, why have we got it? Or you could choose to maintain it because the maintenance costs are relatively small because it's already high quality. The last category is high quality and high business value. So this is software that they've managed to, they use it extensively and they've managed to keep it of good quality. Perhaps because it had really good design in the first place, perhaps because the maintenance team have been particularly skilled about ensuring that patches are fully considered in terms of the entire system, not just the thing that they've been patching or something like that. So in that situation, you would continue using it with usual system maintenance, right? Because it's such critical software for the company and it's relatively low cost to maintain because it being a high quality software. Okay? Because high quality software is generally easy to understand, it's well documented and well understood. Okay, so this brings me to the idea of software re-engineering. And this is the idea that we want to rewrite or restructure either a component of or the entire legacy system without changing its functionality. So the idea of rewriting it in a new language or something like that. And typically you'd want to do that if you've got frequent maintenance where you're having to make a lot of changes and it's becoming quite expensive to make those changes because of the old technology that's being used and the lack of skills for that old technology. So you expend some effort in order to make it easier to maintain. Okay? And while you expend that effort, it might involve restructuring the software to have a cleaner design, and you almost certainly are going to redocument it to make it easier going forward for newcomers to the system to understand it. And I wanted to make the point, this doesn't just apply to legacy systems using old hardware, software technologies. You might do software re-engineering even for systems that are well understood, just because you want them to work with a new technology or interface with a new bit of hardware or something like that that they weren't designed to do in the first place. And in the process of doing that change, you might decide to do this restructuring or redocumentation in order to make it better in the long run. So if we look at the process of software re-engineering, you have the original program and you often do source code translation, either by hand or automated. Okay, if it's very large scale, you almost certainly want to do it automated, but you probably also have a phase of going through and cleaning it up once it's being automatically translated. You might have to do some reverse engineering where you know what the functionality of the thing is, but for some reason you don't have the original source code and you need to re-implement that part of it. Right? So you work out at some level how this was implemented and then re-implement it in a new language. You also go through a process of program structure improvement. Okay, so thinking about, okay, so I'm changing from say a procedural language like C to an object-oriented language like Java or Python. I could just write it procedurally in those languages, but then I wouldn't be taking advantage of these new features that are available to me. So can I change the structure to take better advantage of the features I've got in this language and the new modern software development ideas that have been associated with this different paradigm and that sort of thing. Also, of course, you need program documentation. Okay, so understanding the new code And that's going to be different to the program documentation that was associated with the old code, because you're going through this process of both reverse engineering and structure improvement. You also often have a section on modularization, right? So old software that has developed over years and years and years typically becomes more and more tightly coupled between different parts of the program communicating with other parts of the program, to the extent that it's really hard to separate out individual bits. When you're taught about program design, you're taught about the idea of taking out this part of the system, which talks with that part of the system, and we do those diagrams at the architectural level, where you have things that either a line or a stack or that type of thing, where the interfaces between the different things are very clearly defined, and that we're talking about different modules there. So that's what's going on at this phase. So we then have a re-engineered program, right? But the re-engineered program might also look at restructuring the data that is used within that program. Okay, so you've got the original data, probably quite a history of data that's stored in a database somewhere that you still need to access. Do you want to keep accessing that same legacy database? Probably not. You might instead draw up a new data schema and translate that old data into the new data, giving you that re-engineered data. Right? And then any new data that your program generates or subsumes from something else goes into that re-engineered format, rather than having to use that old antiquated format that was designed 40 years ago or something like that.